In section 6.4, you're looking at sampling distributions, and I think neither one of the PowerPoints, new or old, do a very good job of explaining the process of how you would construct a sampling distribution in a textbook. The idea is that you have three unbiased estimators, the mean, something called population proportion, and your variance. For all three, you're going to go through the same process. What you're doing is you're taking a sample of a population, but you're taking many different samples from the population. So let's say you have a population out in the real world of 1,000. You may take little subsamples of 5 and a whole bunch of them. And then you'll find whatever particular statistic that you're looking for out of that sample of 5. So, and we're going to look at the mean, so let's go with the mean. So you take the mean of those 5 and you write it down. You throw them all back into the pot, you pull out another 5, you find the mean. You take enough of those means of those small samples, and they will trend towards the mean of the population when you find the mean of all the means, right? So you pull 5 out, you write down the mean. That's a stat. You do it a couple of times, 10 times, 20 times, 100 times. Then you take those 10, 20, 100 means and you find another mean, right? Mean of the means. And that, as you pull in more and more samples, hopefully you watch the video, that will give you a better idea of what your mean is for your overall population. Now in the textbook, we're going to work with very small populations. So allegedly in question, I think it was like 3 or 4, you had 3 people living in 3 houses, and that's like all the people in the world. So it's going to be a little bit more cut and dry in the textbook form, but it's also going to allow us to actually find and confirm the fact that those two things represent the same number. So let's pretend that I went to 3 households and I said, how many people live here? And I had 1, 4, and 10. And I want to now construct a sampling distribution for the mean with n size 2 groups. So I'm going to go into the hat and I'll pull out 2 numbers. If I go in the first time, I can pull a 1, a 4, or a 10. I look at it and I say, that's great. I put it back in and I can get a 1 again. I can get a 4 or a 10. And so my sampling space looks something like this. I could have 1, 1, 1, 4, 1, 10. I can have 4, 1, 4, 4, 4, 10. 10, 1, 10, 4, 10, 10. And I can confirm that I have all the different permutations because I got 3 things that happened the first time, 3 things that could happen the second time. If you multiply those guys together, you get 9. And I got 9 little samples. Sometimes they give you the tree, sometimes they already give you the little pairs. Either way, at this point, once you have the pairs, you're going to need to find all the mini stats, I'll call them, right? So if I'm looking for a sampling distribution for the mean, I need to find all these little means. So the mean of 1 and 1 is 1. 4 and 4 is 4. 10 and 10 is 10, right? Because you add 10, divide by 2, you go right back to the 10. 4 plus 1 is 5. Divide by 2 is a 2.5. Unfortunately, it's commutative, so that's also a 2.5. 10 plus 1 is 11. Divide by 2 is a 5.5. Again, commutative. 10 plus 4 is 14. Divide by 2, that's 7. And I have 2 7s. So now I'm going to make my relative frequency distribution table. There's all the means that I can have, and here's the probability that they'll come out. My smallest one is a 1. Out of the 9, that only happens once. Right? If I pull out of this pot. My next one is a 2.5. Out of the 9, that happens twice. My next is a 4. That happens only once. Then I have a 5.5. That's twice. I'm going to need to scroll down. And then I got a 7. He was twice. And then lastly, 10. 10's only once. It is not uncommon for you to get these types of numbers where it's 1, 2, 3, and there's not a lot of choices because we're keeping very, very small populations so that we can find all of these samples. Imagine you had 9 with a set of 3. Imagine if it was a set of 30 and you wanted to take 2. That would be 900. So not fun. So I have all of these means. If I take these and I find the mean of this table like we did in chapter 5, I go into stat edit. I put 1, 2.5, 4, 5.5, 7, and 10. And then 1 came out 1/9, 2/9, 1/9, 2/9. My Math Lab will tell you, or My Labs Plus will tell you, that it needs to be in numerical order. It does not really need to be in numerical order, but there's not a ton of numbers, so it's pretty easy to do. My table's in there, so now I want to find the mean of this table, or the expected value. So it's the x value that I'm talking about, which in this case represents a mean, times my p of x, and then I'm going to add them all up. But I already typed them all in, so I might as well go ahead and use 1var. So I'm going to go stat, over to calc, 1vars. L1 are your values, your frequencies are in your L2. So if you have a new calculator and it says FREQ, that's where you put the L2. Old calculators, you're going to put comma, second 2, and link those tables like we had to do for our chapter 5 lab. Hit enter, and my mean is a 5. So the mean of this table, the mean of the means, I don't know how I would write that, is a 5, which is not terribly surprising, right? Because 1 plus 4 plus 10 is 15. And the mean of that population is 15 divided by 3, by lo and behold, is a 5. So what does this mean? It means that the means are unbiased estimators, which we already knew from the PowerPoint. It means that if you take enough sample means, that the overall mean of the means will target the population mean. In your homework, it will work out perfectly every time that when you find the mean of the table, it will always be magically the number or stat that you were looking for in here. So even if I was looking for a population proportion or a standard deviation or a variance, I would still find the mean of the table because you're taking a mean of all of the little sample stats. That's Penny. So don't get caught up on that. You're always finding the mean of the table. It's not always the mean of the mean. It could be the mean of all your standard deviations. It could be the means of all your population proportions. In the real world, you wouldn't have it turn out to be exactly the same because the reason you do this is because your population is too big. We'll do more of these in class.